Okay, so welcome to Leipzig Gophers 22. It's October 26, 2021, and we are thrilled to have Moritz Eckert from Edgeless Systems talk today about confidential computing in Go. So we are very happy to have you here, and Moritz, please take it away.
Thank you, Martin, for the introduction. Let me share the screen. Can you see something?
Yeah, looks good to me.
Okay. So just to give you the full picture, I'm working for a small startup in Bochum, Germany, and we're developing open source software for confidential computing. And I'm going into those meetups, going into conferences to basically bridge the gap here between, let's say, the more security privacy community that's inside this whole confidential computing bubble, and then on the other end, the Go cloud native community that's building all the software that's running inside the cloud. And to get something out of this whole concept, I guess we have to bring them together and that everybody understands the needs of each other and can profit and can build very cool new privacy enhancing technology for the cloud. So my plan today was to give you a basic introduction of confidential computing on this technology. And please feel free to ask questions whenever they occur. And then I'll just explain a bit on how you write Go software, or how we imagine that you write Go software for confidential computing solutions. And let's see how much time we have left, and maybe we can do a very small excursion into scaling, deploying things in the cloud. So confidential computing, I guess you can very to bring it down to like one single thought is that we can't trust computers, and especially we can't trust computers of other people. And with the whole shift into cloud computing, especially in the corporate world, everybody wants to get rid of their data centers and move all their workloads, all their computational power to the cloud. That means the cloud is essentially somebody else's computer. It might be some data center, it might be owned by some large corporate, but in the end, there's still a lot of tech stack running there that certain people and have access to or write code for, and then there are all those administrators. There are other customers running on the same, or potentially running on the same machine, and there are potentially malicious actors, attackers that might gain access to a certain part of the infrastructure. So you could very much boil all this down to you can't fully trust the cloud, either because you don't want to, or because regulators say so, because you're processing privacy relevant information, some medical data, financial information, all this kind of stuff. So this is the basic statement. And if we look at a very very high level abstraction of the tech stack, you have the application layer. So let's say we are some Go developers writing software that should be run in some cloud environment. Then there's potentially some operating system and hypervisor below it that abstract away the hardware. And then there's the hardware layer. And then you have certain human beings having access to a certain part of these layers. And the goal or the idea is that we can, so in this state, we have to trust all layers in the systems and all humans having access to this. And the goal is that we minimize this trust base. So minimize the amount of components that we have to trust, that our data, our code stays confidential, has integrity, all this kind of stuff. And the idea of confidential computing is that we separate our code, our data, into secure execution environments that we typically call enclaves. So again, we have the same tech stack, but this time we create a secure environment, and this secure environment is protected, is isolated by just a small part of, in the majority of cases, your hardware layer. You could imagine some software layer for certain specific cases, but most likely it's going to be based on some hardware layer that protects this enclave from the access of all other layers, all other components in the system. And this means you only have to trust this hardware layer, that your code, your data can't be accessed by anybody else or anything else. And to formalize this into like some properties, we can say that enclaves are isolated. That means they are isolated from the rest of the system, like horizontally and vertically. So nothing else can access this part of the system. And that also means that the memory, meaning the physical memory. So even if I go to the data center and I pull out the machine this code is running on, I try to peek into the main memory there, I won't have any success leaking data, because the main memory of this enclave, or wherever this enclave code and data are stored, is encrypted at all times, meaning at runtime. So even while this code is running and it's processing your data, its main memory is encrypted. And then if we want to have some kind of persistence, say we want to be able to restart, or we want to store data on a disk and load it back later, we need some kind of we need to basically encrypt it, move it to disk, but then we need some kind of mechanism that when we want to decrypt it, there's some process in place that makes sure that whoever wants to decrypt it is still running inside a secure enclave. So we need to bind the encryption to the enclave's identity, if you will. And the last thing is, while the first three properties are very cool and they protect your stuff and everything is secure, it's a very fundamental feature that we can also prove this security here. So we can show to the outside world that we are running inside a secure environment, or prove to the outside, like from the enclave perspective, or that we can prove to a third party, a regulator, that our app is running inside the secure enclave. While the first thing means that from the enclave's perspective, we can, for example, prove to a client, hey, I'm running inside a secure enclave. You can securely move over your data, and I'm going to process it for you, and everything is secure. And the second notion of like proving to a third party is basically this regulator view that let's say we want to process medical data, financial data, we need to show to the government that our code is always encrypted end to end, and then nothing can ever be leaked. So these are the four properties in a very high level, and the Enclave concept is implemented by different vendors in, let's say, maybe slightly different flavors. The initial idea was basically to say, okay, let's take the approach of like function as a service. So we split our application into several parts, and the ones doing operations on data or handling keys or stuff like this, these we're moving into functions, and those functions we move into enclaves. But this turned out to be very cumbersome because you need a lot of brain power, a lot of energy into developing applications, splitting concerns, and this is very error prone, and data might leak while you move it in and out of those functions. So we then shifted, or the idea shifted more towards, okay, then let's package our whole application. So that means our whole process into a secure enclave. That means we don't need to split the application. Development is easier. And this is where Intel SGX, you could say, is today. So you have a process-based solution. We isolate processes into enclaves, and we can run our whole application from there. And this is where most of the tools or the open source project I've been working on have been focused so far. Intel SGX is the one that's accessible today and most cloud providers. But one thing that you need to bear in mind is that you can just run your regular code inside such an SGX enclave, because it has a slightly diminished system interface. It needs some slightly modified code to run there. So it's not this ease of lift and shift that most people want. And this is why first AMD and now also Intel and also all the other solutions here. I'm not sure about the Apple enclaves to be honest at the moment, but at least the ARM realms and the RISC-V Keystone architecture, they all go more in the direction of basically taking a hypervisor view and then splitting concerns based on whole virtual machines. So you basically have a whole virtual machine in the enclave. And the price for that is that you, of course, have a much larger trust base, because in your enclave now you have the whole operating system code. You have all those services, applications that run in that machine. They are all part of your trust boundary. So you basically get an easier lift and shift for the price of more components you have to trust. And you can see this as an evaluation you have to do. How big you want your enclave to be, and how much like lift and shift you need, how much legacy code you have, and based on this, you can then decide which technology might be for you. The one that's that exists the longest of those, and that is available today, is SGX. All the other ones are slowly popping up. With AMD SEV, I think, is now available on some cloud providers. But to go back to the confidential computing idea, your system, your CPU is providing you with an isolated environment. You can see this as a black box. You move in your data, your code into this black box. It's processed there. You obtain the results. You can then get a proof at two stages. You can get a proof before you move in your data and your code that the black box is isolated, is secure. And you can get a proof that, or you can take the same proof to know that whatever code you put into the black box was executed exactly as you intended. So nobody modified the code. And based on that, you can be certain that your results were not manipulated, at least not in this way. And whenever you need the persistence, you can have a sealed state, meaning you can write your code, write your data to disk and decrypt it later, and be sure that only inside this black box, the sealed state can never be decrypted. Right. Are you having questions on this confidential computing introduction? It was very high level. So if you have any more low level questions, feel free.
Yeah, just the other vendors. This was a question that I had. Like, is it just an Intel thing, or are other vendors like moving towards that? But what is the time, like the time horizon for that? Like, do you think in like 2 years it will be like, or like in the next generation of CPUs in 5 years, they will be like more support for that in other architectures? Like for example, ARM being like a interesting target for data centers and probably will be deployed much more in the future. Is there,
Yeah,
do they have a
I don't.
roadmap or something like
I can't tell you exact dates or
yeah, sure.
stuff like this out of my head, but we definitely see a lot of movement there. So the Intel and AMD already released their architectures today. There's one more thing coming from Intel, I think, somewhere in the next year or so. The ARM realms, I'm not sure when they. I think it's also going to be like the next 1 or 2 years. It's always this time frame of like in 2 years or so. But we definitely see a lot of movement from the hardware vendors to go into this direction. And part of this, and this is what I want to go on the next slide, is because their large customers, the hyperscalers, they all are moving into the direction of offering confidential computing. Because for them, as well as for you, this has a lot of advantage. They can get themselves out of the loop by saying, okay, you can move even more workloads to the cloud. You can move your I don't know, your intellectual property. It might be some trained machine learning model, or you can move your the data of your connected cars to the cloud. You don't need to build your own data centers for that. You just use our confidential computing solution. It isolates this from the rest of our system. We can peek inside, nobody else can peek inside. And this basically enlarges their customer or the user base. And there are even some voices in there saying this is going to be part of the fundamentals for the future of cloud computing. So it will be transitioning more and more into everything will be confidential computing. It might not be SGX-based process enclaves. It might be that just every virtual machine, and that means also every Kubernetes node will be running on some confidential computing machine. So yeah, I think I can tell you an exact time frame, but it's gonna be in like the next 2 or 3 years. Almost all of this stuff is gonna be present in hardware and in the cloud.
Yeah, interesting. Thanks.
Actually, I have a question. I'm not sure if you explained already, but when you have data that's inside this enclave, and you have code and data that's outside of the enclave.
Mm-hmm.
But if you need to work with some secret data, if I understand correctly, at some point you would need to pull it out of the enclave and work with it on your CPU to do stuff. So how would you keep it secret at that point? Because once you pull it out, it's no longer encrypted. If you're working on, like, it's being pushed around in memory or on your CPU or something.
Oh, so okay, maybe I didn't make this clear enough. So basically, what you have without confidential computing, as you said, you have encryption at rest. So let's say the sealed state. You have some encrypted data on the disk, and then you have you can encrypt it in transit using TLS, using some form of transport encryption. What the black box means is whenever you move this encrypted data into the black box, this means that the black box is basically while you're executing it. So while it's not homomorphic encryption, so it doesn't stay encrypted while you're processing it. It's decrypted, but when it's decrypted, this only ever happens in this isolated part of your system. So
okay, so all of your transformations of whatever data that you're doing with you put the code as well as the data into the black box. Is that right?
Yes.
Okay.
So think of it like a regular. So if you talk about Intel SGX, and this is going to be what I'd like to talk about today, and what we are doing mostly. You can think of this as a regular Linux or Windows process, But this process is completely isolated from the rest of the system. So as soon as this process comes up, everything is encrypted on the hardware layer, and it's isolated. So no other process, no system, no operating system can peek inside. And this is implemented on the hardware layer on the inside the CPU. So the CPU is actually doing basically a context switch to, okay, I'm now running a secure enclave, as well as on the memory access, right? So you have certain encrypted pages that belong to an enclave, and only this enclave can access those encrypted pages in your main memory.
Okay, and so that would be at like maybe a higher level of privilege than say ring 0 or something?
You could probably say that, yes.
Okay.
Okay,
yeah, that makes sense.
The importance here is not to misunderstand, right? A higher privilege would mean also that you from the enclave perspective, you could peek into your operating system and stuff. So this is
no, I don't mean that way. I mean just like the operating system could not peek into the enclave. It doesn't have enough privilege to be able to get in there.
Yes. Okay. Further questions? All right. I guess maybe questions come up later when we talk about how we do this with Go, and it gets more practical and more accessible, I guess. Just to give you some existing examples of things that use this today, so you get an idea of what you could do with that. One very prominent example was Signal. I guess they were one of the first using SGX technology for something that runs in production. So the idea was that they wanted to offer contact discovery. That means if you install Signal, like any other most messengers like WhatsApp, Telegram, and whatnot, they would tell you, hey, can you give me access to your contacts? And if you click yes, they say, okay, those people are already here on WhatsApp. Do you want to message them? And how do they do this? To be honest, I don't know the concrete implementation of WhatsApp or Telegram, but most likely what they're going to do is they're going to upload your data compared to their database, and to give you those informations. And Signal, of course, being very privacy aware, they didn't want to move your contact list to their servers with the potential of exposing your contacts. So what they came up with is they created a server backend that's running inside a secure SGX enclave. So they load your contact list into this SGX enclave. That means your contacts list is never ever leaving. It's basically only on your phone and inside this protected black box. And then they load their I don't know, their customer database or whatever, however they store their contacts, and then they compare, or somewhere along those lines, and then they can give you those information of who's on Signal and who's not. And this is very cool because they can give you this feature, this convenience, without ever revealing your contact list to anyone. The other very prominent example, at least in Germany, is that we get electronic prescriptions, electronic health records, and medical data is always something people are very careful with, and right so. And most of this back-end software that's actually dealing with your electronic health records, that are dealing with who has access to or processing data into that direction, they need to be run inside secure confidential computing enclaves. And this is being done I guess mostly with Tls GX, but I don't have any concrete insights other than that. Right. So the most use cases can be differentiated into making existing apps more secure. This is going in the direction of lift and shift. So you have something that you're running on your local IT infrastructure that you're shifting into secure enclaves, and then you can move them to the cloud and make sure and be certain that nobody can access the data. And then there are new applications, things that were not possible so far, and this is something I personally find very exciting. Things that couldn't be implemented so far, like a lot of those multi-party things. Like if you want to collaborate on, I don't know, on research or on identify money laundering in the financial industry, and you want to collaborate with different financial institutions, and you are don't want to or not allowed to share your data with each other, then you can build those systems similar to like how Signal does it, where you pool your data or you process your data together inside secure enclaves. You define the code pre-hand, you deploy this somewhere in the cloud, and then everybody uploads their data, and this is processed inside the black box, and they all are provided with the results, and no single party needs to be afraid that the other party might leak their part of the data. And you can come up with a lot of more examples going into this direction. Yep, these are use cases. I hope this gets a bit more, makes it a bit more clear of how we see this technology and how people envision how this technology is used. So to make this more practical and to bridge the gap to cloud native and Go, we have 3 open source projects we are working on. The first one, and this is going to be the prominent one I'd like to show you today, is Ego, basically building Go microservices for Tls GX enclaves. And then we have something for solving a lot of the problems you have when you're using microservice architectures and deploying this in the cloud. And something that we identified as a missing piece was we needed a secure database that's not just encrypting data on disk, but also encrypting it at runtime, so you can use a regular MySQL interface, and data stays inside enclave boundaries. So very high level overview of Ego. The goal of Ego is Go applications into SGX enclaves with as minimal changes, as minimal adaptations of your regular Go developing process. That means we'd like to have 0 code changes. We'd like to have almost no, so you don't have to think about much about what into SGX enclaves are, how you go from a Go binary to an SGX enclave binary, and all this kind of stuff. This we try to hide behind Ego and make your life as easy as possible. To do so, we need to modify the Go compiler slightly, because we need to compile code that is able to run inside SGX enclaves. And as I said, they have a slightly diminished system interface. That means you can't have all the syscalls you have on, for example, Linux. And our Go compiler is adjusting for that. And then we basically abstract away the process of going from your compiled Go binary to the fully fledged enclave. And we wrote some Go libraries that make certain Enclave functionalities accessible to your Go code. That means remote attestation, for example, sealing, and I'm going to go into some examples of that so you get an idea. Before I'd like to show you some examples to peek under the hood of what's happening there. So don't worry, you don't need to actually understand all of this, but just that you get the full picture. What's happening when we do the compilation step? So you normally do go build, or you might do go build, and with ego we just have the ego prefix. So it's in this case it's ego-go build. What's happening is we compile your code, but instead of just basing it on libc and all this stuff, we also base it on our runtime. That is basically a Go C++ runtime for SGX enclaves based on Open Enclave. That's a Microsoft project, and all we do is compile this code based on top of Attested RT. So it some syscalls, instead of issuing the syscall directly, they will transfer the execution flow inside Attested RT, handle the syscall there, and or potentially handle an enclave exit and an enclave entry from there, and dealing with this. That also means, as a fun fact, that you could run this compiled binary also on your regular machine. You don't need to run it inside an SGX enclave, as long as you don't use enclave specific functions that are only available in enclave. So if you want to get a remote attestation statement, this is not gonna work. This only works inside the actual enclave, but the regular Go code is not modified, so it still runs as before. And if we do the packaging, we call this ego sign. So it's the command to go from a compiled Go binary to a fully fledged enclave. This takes your enclaves, takes your Go code, and has an enclave skeleton that consists of a very small init, which is more or less just setting up the enclave, setting up the Go runtime, and then transferring execution to your code. And it's signing the final binary blob with your private key, because all code that runs inside SGX enclaves always needs to be signed. The idea is here we have a black box. Nobody can peek inside. If somebody needs to run this black box, that might be some cloud provider or some other system, they need some way of verifying that this black box comes from you or comes from a trusted party. Otherwise, there could be a lot of malicious potential here. So we package this, and then we sign it, and then you have a signed SGX enclave, and then you can run it like we normally would do. But for example, go run, and then in our case, then it's ego run. And this is all, right? So you don't have to worry much about the SGX part. You focus on writing your Go code. You use the Go ego build and the sign command, and you end up with a fully fledged enclave. So this was the peek under the hood. Not sure if you have questions on that.
Yeah, actually, I do have one question. You had mentioned that it does forwarding of the syscalls.
Yes.
Does that add very much overhead?
It kind of depends on what the syscall is doing. Some stuff we can basically directly handle inside the enclave. If you're doing a lot of I/O operations, we need to, of course, interact with the system, and this basically means that because SGX is a process-based solution, this means your enclave or the execution flow leaves the enclave. So it's a context switch in the SGX world, a context switch to the unsecure world, some execution flow there interacting with your host system, and then a context switch back to the enclave mode. And these context switches are, in fact, can be in fact expensive. So it's a bit depending on what systems calls are happening there. But since I think the Ice Lake architecture of Intel, they increase the accessible memory of SGX enclaves, and this has highly reduced the context switches based on mapping of pages and stuff. So with Ice Lake, SGX has a much better performance than it did before. But the exact overhead is a bit dependent on what you're doing inside the enclave.
Okay, so actually that brings up another issue with I/O. So I guess that means that since I/O is going to go outside of the enclave, then you also have to be really careful about what kind of data you're passing via the I/O calls, right?
Yes, yeah.
Okay.
And speaking of memory, excuse me.
No, so go ahead.
Speaking of memory, you said that an architecture increased the memory limit that is kind of usable for an enclave. What is the limit, or like what is there a hard limit, or what?
That's a good question. Before the limit was rather low. I'm always bad with these numbers. I can't tell you exactly, but it was less than a gigabyte. That I know. And now I think it's there is a limit, but it's very big. I'll have to peek into the spec to give you the number, but it's most likely going to be sufficient for whatever you're doing inside the enclave.
Yeah. Just one other very high level question. I just saw one example in the Ego repo, having a HTTPS server running, basically receiving some secret, but the server itself, as far as I understand, runs in an enclave, and so that would be like a transfer of secret data to a server without the host environment being able to read that, for example.
Yes.
And so this sounds really great. Is it possible, maybe you want to run at some point all your applications in such an isolated mode, or is it because it's just more secure, gives you just more isolation in general. It's just a silly, is it a silly idea, or is it something that you would have to consider based on the overhead that you're adding currently, maybe as far as performance goes or stuff like that? Because just ultimately, this would be ideal for every process that is running, being just very secure and not being able to just close out all the kind of threat models that you get otherwise, or something like that. But
I see where you're going there. There are a few different angles you can have on this. So one part is, of course, if you move something to an enclave, you certainly might, let's say you might have some performance impact. So one thing you might be considering is performance. The other one is that it can add a security perspective to it, depending on where you deploy it and what your threat model is. But then there's the point of, if you move everything to an enclave, basically you might end up with just a large TCB. So like you have, because everything is running inside the enclave, you more or less have to trust everything again. Or the other direction, you need to verify everything. Yeah. Because it also depends on why you're using this. So if you're just using this for yourself to isolate yourself from the cloud provider, then this might be a viable option. And this is somewhat where the confidential VMs are heading, because they move everything inside secure enclaves. If you're trying to build an application that's communicating with the outside world, and the outside world needs to verify, before they want to shift data to your application, need to verify your thing. If you have everything inside secure enclaves, you might ending up with like verifying everything. And also consider that if you change part of the code of your Go application, this completely this needs to be re-verified, right? So you change just one line of your Go application, repackage everything, deploy it. From the outside world, it looks like at the first glance, you just see, oh, it's a different enclave, different measurement, and then you need to verify, and then you need to basically go from, this is the enclave code, this is the corresponding source code. Okay, there was just one line change. And this is feasible if your TCB is small, but if you have everything inside enclaves, this might explode and becomes unfeasible. Just to give you some thoughts on this. Okay. But you're right, of course, it could be a security benefit.
Yeah, I can see, like, yeah, great. I think it's a good perspective. Like you want to have like some semantics of like what parts are secure and performance overhead and the various aspects. Yeah, thanks.
Yeah, I guess with confidential computing, you always have to think about the goals, the threat model you're working with, and then basically this can decide of what direction you want to go, going more into like the Intel SGX, going more into the confidential VMs, and what parts need to be run in enclaves, and then what part shouldn't be cited in enclaves and stuff like this. Okay, so you were mentioning the Tls server we have as an example for Ego. My plan was to actually take a look at those those samples and maybe explain using them a bit more of what it could mean to write Go software for SGX. I have a VS Code window. I'm not sure if this is large enough. Increase it a bit. So this is the Ego repository. You find it on GitHub, but I've opened it in VS Code, and there we have a sample folder. Basically, just very small use case examples and a hello world explaining how to use Ego. And the hello world is, I think, taken from the tour of Go with a very simple loop saying hello world. And as I showed on the one Ego in a nutshell slide, if you would take this Go code, you would probably do go run hello world. Oops. I haven't used Go. Isn't it Go run? Ah, I'm not in the hello world.
Yeah, should.
Ah, okay. I was confused. I haven't used plain Go for a while now. Okay. So you can also do Go build of the same thing, and what it will do, it will compile it to binary code, and you end up with a file hello world, and this is your compiled Go code. And as I said, with Ego, we modified the Go compiler. So we do Ego build hello world, and it does the same thing as your Go compiler, just slight modifications, and the same thing will pop out of it. It's not the exact same binary, but it's still a binary that you can run on your local system. And to go from the binary to the enclave, I said we need to do the signing step. So this is abstracting the whole process. So you just do ego sign hello world. And what we will see is the binary stayed the same. So ego sign didn't modify the actual code anymore, but we see 3 new files. JSON, enclave.json file, and 2 keys. So the enclave.json allows you to modify some variables of this enclave. And when there isn't an enclave.json, the first time you run ego sign, it will generate one, and it will also generate a pub key pair that it's used for signing. And when you would, in your regular development process, would have your secret signing key that's signing all of your enclaves, you could replace this file here, or replace the private PEM with your private key. And then you could do some configurations, some enclave information about heap size, product ID security version, and then some ego specifics about mount points. So you could define that your enclave should mount some files of your host system, or have some mount points of your host systems. You could define some environment variables and some actual files here. And then if you modify stuff here, so let's say I do product ID 2, you have to rerun the signing procedure. And then what's happening when you do ego run is it's loading your it's basically loading our enclave skeleton and loading your hello world binary inside the skeleton, and then running it. And we can also show some information about like who signed this enclave. So who's the owner of this enclave, and it's gonna show us information about your public key. So if I do signer ID on public.pen, it's giving me the same output. So I see that this enclave was signed using this key. Right. So this is the basic build process using Ego. We have one additional step to your regular process where we go from enclave binary to actual from Go binary to actually enclave, and we can modify the behavior here using this JSON configuration. And this is let's say the boring part about Ego. I mean, it's very cool because it's very cumbersome to build the enclave yourself. And the sign step is actually abstracting quite a lot. So this is very cool, but it's also not much you can see. There's not much happening here.
Actually, I do have a question.
Yeah.
So this is running the entire program, the entire Go program inside of the enclave, right?
Mm-hmm.
But for a normal application, would you be running the enclave stuff like as part of the process to isolate one part of your process from another part of your process, or would you have one as a completely separate process and you just communicate between them?
So what this was the original idea of SGX, that you split your application and you only move certain parts into the enclave.
Mhm.
But the ego and most people, or let's say almost all people using SGX today, shifted away from this pattern and just moved the whole application inside the enclave and only split, let's say, on a microservice layer and not on the single application, single service layer. The reason being that splitting the application was very tedious work. I see there are definitely security benefits. So from a security mind perspective, this can definitely make sense, but it puts a little load on the developer, on the architects to think about what parts, what functions do I need in the enclave, and then they need to make sure all those transitions, like where data is flowing between unsecure and secure world, are always making sure that the data is only leaving the enclave encrypted. And there turned out to be a lot of errors happening there, and development was rather slow. So this never really took off. So it's moving into the first thing you explained, where everything is inside the enclave, at least for a single application. And this is also where Ego is going, or what Ego is doing.
Yeah, I guess well, with the microservices architecture, you've already isolated so much of it anyway. So it would just make sense that some of your microservices are secure enclaved and others, which are not as important, don't have to be.
Right, exactly. And this is exactly the idea behind the Ego as well. Yes.
I've seen that you've run in simulation mode, and this is how I got also the code running, because when I did not have the environment variable OE simulation set to 1, I would get like some error, although I'm like I'm a newbie, like I just enabled SGX in my BIOS, and but I cannot run, but I need the simulation mode. So what would be like, there's a platform error or some kind of thing, but you're running it also in a simulation mode. So why?
Yes, this is you're right. So to basically to run it without, so simulation mode is basically based on, we're using Open Enclave, and Open Enclave has a simulation mode that even though you don't have SGX available in the system, you can still use it. If you don't, if you have SGX available as a hardware technology in your processor, and if you're running on your local machine, this is going to be less and less the case, because Intel is removing this technology from your consumer CPUs and only deploying it to the cloud. But no matter what, if you have it, you need to enable, as you said, in the BIOS, and then you need to install the a kernel module to expose it to your user lens. So it will basically show up under /dev/sgx. The kernel module was originally maintained, developed by Intro separately, but since kernel, I don't know, 5, I'm not sure, 5 something, they merged it into mainline. So if you have a very recent kernel, you might already have the SGX kernel module in there. And in Ego we have, one sec, we provide a Debian package for installation, but I'm not sure.
Yeah, I think I used that.
This is installing the prerequisite. Basically, it should install Attested RT, but I don't think Attested RT is taking care of that you actually have an SGX device installed. Let me take a look at Attested RT.
Yeah, I think I used the Debian package, and it was not, the device was not showing up. Okay, so probably I missed the kernel module, and I should install that.
Yes. I might be able to point to the explanation of how to set up. There's also an info page on how to set up SGX on your system.
Yeah.
I'm not sure if I see it here. I think it's the dep installs the runtime and everything, but it's not installing the device on the system.
Okay, yeah.
But there's a second part to this to this answer. Even if you get it to run the Hello World on your local system, basically Intel switched the way you do remote attestation, and one of us going to do this in the next sample. And that means that they basically differentiate if you're running this in a data center, and that means in cloud, or if you use their legacy remote attestation system. And because basically everybody is using the new data center attestation primitive, all the samples and ego is only supporting the data center attestation primitive. That means in your local system, you won't be able to use all those attestation examples, because for those you need to have some kind of attestation set up. But let me show you with the example what I mean. Oops. Oh, this was not intended. Right. We have the examples. We have the attested HTTPS server and the attested HTTPS server manually. And I'd like to maybe start with this one, so you get the idea what the other one, where the difference to the other one is. And I think this is in remote attestation. So the idea is, I think Martin said this before, that he tried the web server that's using remote attestation for establishing a secure connection. So the idea of this example is that inside the enclave, you're running a HTTPS server, and then you have a client that wants to verify first that this is actually a secure enclave I'm communicating with, and after that, establishing a secure connection and then exchanging information. And so far, there's no like attested TLS or attested HTTPS as an official standard. In fact, there's actually a paper from Intel that's proposing something in this direction, but so far it doesn't exist. So we are doing this, what you might call an attested TLS, manually here. And the idea is that we generate a private public key pair, and then we obtain a remote attestation statement from SGX. And SGX remote attestation statement saying basically, okay, the CPU is creating a short report saying, yeah, this is enclave, this is a secure enclave with this measurement and signed by this key and some more variables. And then it has a payload that was provided by the enclave. And in this payload, we put the hash of our public key. So we basically get a remote attestation statement saying, yeah, this is us. This is the enclave of our identity, and it has this public key as the payload. And then we take this remote attestation statement again, and we put it as part of our TLS certificate that is exchanged during the HTTPS handshake. So whenever a client is connecting, it's doing the TLS handshake, it gets our TLS certificate. And part of this TLS certificate, we have this remote attestation statement. And if the client is trying to do remote attestation here and is aware of this, so if you have the corresponding client side, it can pull out the remote attestation statement, can pull out the hash, take a look at the certificate, like take a look at the public key, compute the hash, and compare it to the one in the remote attestation statement. And then what we end up is we end up with a public key that we can trust because we have a SGX remote attestation report containing more or less this public key. So we're binding the attestation report to the key. And then the key can be used to establish a secure connection. And you can always be sure, okay, this key comes from the secure enclave. I can trust this connection. I can trust the other side to run inside the enclave. And this is what this example tries to do. So it creates creates a certificate. And CERT is a bit misleading here, maybe. So it's basically, yeah, it's calculating the hash of the certificate, which is more or less the hash of the public key, and then it obtains a remote report from SGX. And this is something that's coming from Ego. So Enclave here is part of the libraries that come with Ego that I mentioned. So it's basically Enclave-specific functionality that we expose to Go. And if you go to our docs, so docs.edges.systems/ego, we have a reference for the Go library. And this was part of the Enclave functionality. And inside here, we have the function get remote report. And this is basically calling the SGX device saying, hey, I need a remote attestation report. Please include this as the payload. And this is the report data. And then we have the report containing the hash. And we just start a regular HTTPS server. Yep. And I was one step ahead. I was already describing the next step. In this step, we don't include this remote attestation port as the TLS certificate. We expose it at a different endpoint. So we expose the remote attestation statement, including the hash on /report, and then a client can connect to this, obtain the attestation report from there, obtain the hash from there, and then do the attestation from this one. And the client side, on the other hand, when it's connecting to our server, it will obtain the certificate from one endpoint, obtain the report from the other endpoint, and then it has a verify report function. And this again calls some Ego specific an Ego library. In this case, the client side. So this was the Enclave package, and then we also have a client package, and there you have the verify remote report. And this verify remote report, if you are the client, you need some way of basically, you don't know what a valid SGX attestation statement is. So you need some way of verifying the signature of that the CPU the CPU provided to the Enclave. And this is what I said, that Intel basically switched their attestation architecture. But basically what the end result will be is that you have some endpoint on Intel that you can obtain the root certificate of Intel, and then using this root certificate you can verify remote attestation reports. And this verify remote report function is basically doing exactly this. It's very similar to what your browser does when you get the green lock. It has a ground truth, And in your browser, it's all the root certificates that are present on your system or on your browser. And here it's the root certificate of Intel in the end result. So you can verify the remote port. And then you can, after you verify that this is a valid report or like a valid attestation statement, you can pull out the hash, and then you can verify that the hash corresponds to the public key or corresponds to the certificate that was provided by the server. And this basically then verifies that the information inside this attestation statement, meaning the signer ID, which is basically as I showed you before, the signing key of the enclave, is the one you expected. So you can verify that this is actually an enclave signed by us, for example. And then you can also verify the product ID, the security version, so you know this is the exact enclave I'm expecting here. You can also use it's called the unique ID, which is basically the exact measurement of the enclave. The difference here is if I use this triple, I can say something like security version needs to be bigger than that, less than that. But the exact instance of the enclave, like the exact measurement, can change. So if I do an update, I might change the security version. But if I say, okay, security version needs to be bigger than 3, and I change from 4 to 5, this is still going to pass. But if I want to make sure this is the exact instance, the exact build of this enclave, I could verify that the unique ID is equal to some value, and I would pin it to an exact instance of this enclave. Okay, so this is the client server example. I won't be able to run it on my local system here because on my local system I won't be able to obtain a remote attestation statement that works with the new data center attestation infrastructure of Intel. I can run my client on the system and then run the server on a cloud instance on Azure, for example.
Just relating to the comment on usage of SGX, like for example in Signal, this would be like how Signal could do that. For example, like having an endpoint that would do this attestation, for example, in order to get like data into their server to kind of do the comparison securely, for example.
Exactly.
Without going into detail, but like roughly in kind of, okay.
Yeah. Yes. So on in their back end, there might be some HTTPS server that's doing exactly that. That's binding a TLS session to an attestation statement.
Yeah.
Yep. I have some cloud instance, so we can actually try this. Let me go into samples, remote attestation. Ego build. And then let me peek into, is there something I need to be aware of when running this? No, I can just do, I see. Okay, so I can just do ego run here. So this is now starting the server, and on the client side, oh, don't mind about the, this is just complaining about some logging. So this is running inside Azure. Azure is basically implementing the new data center attestation primitive from Intel, and they have some client libraries to talk to their attestation backend. That's more or less just a proxy to info. But I don't want to go into too much detail here. And sometimes if I haven't set up logging correctly, it's complaining. And on the other side, go to samples, remote attestation. Go build. Should be client here, and client gets the, as an argument, it gets the signer ID, and this signer ID argument is then passed to the verify remote report function, and then is used to compare the actual signature of the enclave. So if I if I parse in the if I use ego sign ID on the public key that we used for signing this enclave, as it's done here, it should pass. So if I do this, it's just outputting send secret over attested check. So this worked. If I would use, let's say, the signer ID of the key I generated here on my local system. So this is not the key used to sign the server enclave here. If I would use this instead, it should complain that it was an invalid signer. Similarly, if I would modify the enclave.json here and say my security version is now 5. Remember that a check security version is smaller than, I think, 3 or something. Check the client code. It checks. Oh no, if it's smaller than 2, it says error. So if I say this is security version 1, and I have to re-sign this, so it's basically repackaging. Server. And run it again. This is running the new server with the new security version being 1 now. And I use the correct sign key. It's still complaining that the security version is incorrect. So just that you get an idea of what you can do here, and how this plays out. In the advanced example, what's changing here is in the server, we basically expose 2 endpoints, assert in a report to do the manually binding of certificate to remote attestation. And as I explained, because I was 1 step ahead, we also have a function in our library that basically does that for you. So you can get a TLS configuration that has a certificate that contains a remote attestation report for its public key. And then on the client side, I have the client function of this tuple that is expecting a TLS certificate that has a remote attestation report in its body with the attestation on the public key. So this is making your life a lot easier. You can just obtain a TLS configuration here. Start your server like usual. You don't need any special endpoints. You don't need to make care of exposing your remote attestation report anywhere. And on the client side, it's very easy to verify this. And this works exactly the same. We provide you here with a callback, and there in the callback you can verify. You can do whatever you want with this report and do whatever you want to verify. So the similar as we've seen in the previous example. Okay. So summary, I guess, is we have the CLI, the ego CLI, that's trying to abstract as much as possible away that you're working with SGX enclaves and try to make it feel like you're working with regular Go code, regular build process. Something I didn't mention here is we have a vault, a HashiCorp vault example. We also have a mode where you basically, if you have an existing project with an existing makefile infrastructure, you can just instead of doing make, you can type ego make, and it will replace all those Go compilation steps with ego compilation steps. So it will automatically compile everything. Then you still need to add the ego sign because we don't know what will be the final binary that's going to be your enclave. But it's basically helping you with existing build pipelines to inject ego there. But that was just a side note. So we have the CLI, tries to make it as easy as possible to work with the build process. And then even more excitingly, you have this library that's giving you access to all the enclave code. Without this library, you can just write. You're basically limited to having limited to existing Go functionality. And with this library, you can actually then use the cool features of remote attestation, establishing secure connections to your enclave and stuff like this. And yeah, I think that's pretty much the summary of what ego does and then how ego works. Do you have further questions?
Yeah. Yeah, that's great. To be honest, I feel much more enlightened and have a map of like where these parts fit in. So thanks for that. I just want to ask like one or two questions. You said like you modified the Go compiler.
Mm-hmm.
Is it something that you like track, like Go releases like a new minor version every couple months or like weeks maybe at times? Do you track that, or do you need to track that, or is it like automated, or like how much? Yeah.
Yeah, unfortunately, we have to basically track the Go compiler releases, and then also release a new ego Go compiler version.
Yeah,
it's not normally. There's not much. There's nothing that changes that affects our changes. So it's very fast, but it's still a manual process so far.
And you do like your own releases, like you're on 0.3.2 at this point, I think. And
yes.
And okay.
I think
and you just
I think we don't we don't release currently. We don't release with every like if there's just a minor release of the Go compiler. It's not necessarily that we also release a new ego version containing this change.
Okay.
But if like the user base of ego would grow and there would be I don't know, somebody wants to use or needs the latest update of the Go compiler, yeah, that might also be possible. So far, we only update the compiler whenever we also change things in ego, or to security or some other thing, of course, if it's a major change.
Yeah. And another question, Go being a like, very popular language with the cloud and, running microservices, whatever. Like, I mean, I have no clue. Like, I'm not in this security security community that much. But a project like yours, like, would it be something that the Go compiler could do itself? Like, a lot of people write microservices. Could they kind of take this in their like main repo? I mean, it's just like, would it be something that would be interesting to them? Like saying, okay, you can run a certain like you can run these steps for your microservice and for the cloud and for Google Cloud or the other clouds or whatever. I mean, it's kind of your project, and of course,
no, I see your point.
Yeah.
Yes. So we build Ego not just because just for fun, but because exactly most of the stuff in the cloud native is written in Go, and this is the way we wanted to build software, because we wanted to build CC software, we wanted to build it for the cloud, we wanted to build it in a cloud native way, and of course then we need Go inside the Enclave. But we have to say that still, even though there's a lot of hype around this topic of confidential computing, the actual usage and people actually working with this hands-on is still very niche, and it's slowly getting traction. But I would say it's not at the point where the Go community would. We haven't tried, but I think it's not the point where the Go community would integrate this into like the main Go compiler, just because this is something still very, very small and very niche. But in the future,
yeah,
that might be, of course, might be a way to go with at least the compiler part of Ego. I guess we would be more than happy to have this off our hands and having this part of the Go compiler.
Yeah, I mean, maybe whatever happens, like I mean, things start small, and I mean, could be much larger in a few years.
I mean, for full transparency, I guess you also have to say this is not anymore the only way to use Go inside the Enclave. So with SGX, something that has emerged, because people are very hesitant for code changes, and people want lift and shift and don't want to think about too much of like the CC tag and that's below. And so what has emerged is so-called library OSs. So more or less, you're creating a full compatible operating system layer inside the Enclave using libraries. So that's to be what you call a library OS, and then run unmodified Go inside there. What that means is you have with library OSs in general, you have a larger trusted computing base, because you have a lot more glue code to build this whole system interface.
Yeah.
And most of the stuff is written in C and C++, so it's not, from a security perspective, it's not beautiful to do that. But you'll be able to then run everything unmodified, and everything without like thinking about CC. When with Go, we try to make it as minimal as possible. It's still, you have to adjust your build process and think about this stuff. You don't get the system interface for Go, like the SGX interface as we provide with the libraries. But you can run unmodified Go code with those libraries. So just to give you the full picture, there is other ways of doing this. We believe the fastest and sleekest way is going more. But if you want to run SGX, is going the Ego route. But there are other options.
Yeah, I think one wonderful part of your project is that it makes something like I read, like I watched or tried to watch a YouTube presentation on SGX, like from some Intel engineer, I guess, and like it's a very complicated topic and it has a lot of aspects. And I think your project does a terrific job of like bringing this down to a couple of steps. So that's certainly amazing. And
Thanks.
I had like one other question. Just maybe as a like fading out a little bit, like one paper that I found was ransomware key management using SGX from like a year ago, 2 years ago, something like that. Just telling like, the bad guys are also happy about more ways to make sure that nobody can kind of get to their key that they use to lock up your system or something like that. Do you have a, like, you know,
Yeah.
as with every technology, of course, you have like various actors, but do you have a take on this, or like, is it something that is important
Yeah,
in some way, or?
That's that's actually an actually interesting topic. I guess this is when SGX first popped up and the whole notion of computational computing popped up, there were like two major concerns. One being this is used for DRM on your local machine, and the other being this is used for malware, for ransomware, and there's definitely potential for misusage here. I guess you have to make it clear, Enclave code can never be privileged code, so you can't run system components inside there. It's only userland. But of course, you can hide, and also the code is always like the thing that's loaded inside the enclave, that's always accessible in plain sight. When the things that you want to have be confidential, they need to be loaded dynamically. But in case, as you said, ransomware key management, the key is the thing that's going to be moved inside the enclave dynamically. And yeah, and this unfortunately was useful to those people for hiding their ransomware keys. And yeah, unfortunately, this offers these malicious practices. Yeah.
Yeah, not sure like anyone else has any questions. If not, then I would like to thank you for this great introduction and great walkthrough through the whole topic. I can only speak for myself, but it certainly kind of cleared up a lot of points for me, and I feel much more confident, like knowing how to, like, maybe not knowing how to use it right away, but like just maybe having an idea where to set something like this up, or where to use it.
Yeah, thank you.
Okay, so I just stopped the recording for the